what the basic von Neumann architecture is. Essentially all computers today are running a von Neumann architecture. There's been a lot of discussion that, yeah, we've made a lot of advances and we're able to do some pretty wonderful things with a lot of memory and all the rest of that. But we're kind of pushing the limits of the von Neumann architecture. And so there's a lot of discussion about needing to look for something different. So that's something that may come up during your career lifetime. But at the present time, this is where everything is pretty much built. So you need to know that aspect of it. That's really the essential part of Chapter 4. The other thing that's in there is this instruction cycle. Different writers will break this instruction cycle into different groups. But the way they've done it here is pretty good and pretty descriptive. The first step, of course, is to fetch the next instruction that has to be executed. Then you have to decode it. The book does this as the address evaluation. Basically, what we're talking about here is where are the operands. And we have to fetch the operands. Execute the operation specified by the instruction, and store the results. Okay, this book separates that cycle into 6 steps. Not all books do. Some, for example, will combine these two into one, and these two into one. But it's a pretty good description of how things work. Okay, so that's really, in a nutshell, what you need out of Chapter 4. Chapter 5 gets us into the LC3. There are a couple of things out of this. First of all is the instruction set itself. A copy of that instruction set on the inside back cover is attached to the test. Okay, so you don't have to memorize that. If you work with these things enough, you get where you know them. You don't have to fuss with it too much, but I included it there. Basically, what you need to know is what does each one of these things do? What would I use it for? And such other things as which ones set the condition codes, so that you know how to set up a conditional branch, things like that. The other thing in here that's important are the addressing modes. There aren't very many of them on the LC3. Some computer systems will have as many as 16 different addressing modes. We have immediate, or sometimes called literal, where the operand is in the instruction. As in add, this is immediate mode. Obviously in there we also have register mode. Let's just label this. This is immediate. This is register. Those are the two easiest ones to work with. The next most common one is PC relative, and is where you give an address relative to the current contents of the program. This is used remember, if you just reference a label here, what it actually stores an offset relative to program counter. That's what we mean by PC relative.
Meaning that you would add the offset to the PC counter.
Right. Yeah, that's the idea on PC relative. There's a base plus offset, which works very much like the PC relative, except that it doesn't use the program counter. It uses a specified register. Distinguishing between these two is actually done in the opcode of the instruction. See, this load works with an offset from the program counter. If you do LDR, uses the contents of this register plus this offset to find the address of what's going to be loaded in. Well, we always used to do these things. If you put parentheses around a register, that means the contents of that register. Plus 3 in this case is going to be the address of the data. functions just like PC relative, except that you're using a different, you're not using a program counter, you're using a fixed register.
And an address is loaded into R2 at the time that you access it?
If you're gonna use it this way, yeah,
Yeah.
you have to load an address in there. Doesn't do it automatically. And everybody's favorite, indirect. If you think about it this way, all of these modes, you're going directly to your operand. Either directly to it within the instruction, in a register, or you compute an address here and go right to the operand. Indirect, you go out and then one more. So you're getting indirectly to the thing that you're looking for. Again, that's specified by the opcode. It's really only used by load and store. Load and store are the only ones that use indirect mode. Okay. That's a pretty quick view at chapter 5.
Let me do a review on the indirect real quick. Pretty sure I got it, but I don't want to assume.
Well, the example that we've been working with has been this idea of you have this sort of thing, which now, if we look at memory, for the sake of discussion, let's say that this is at location 3020. So up here at 3020, I am storing here FE. Now that location is down here someplace in memory. And someplace up here, I have the instruction, load indirect register 1, KBSR. Okay, what's actually going to be in here is an offset from this location to this one. So I go from here, I go out to, let's see, I suppose that's at 3018. This location in here is going to be 3019. So that instruction is actually going to look like this. The load indirect is 1010. My destination register is register 1. And then the other 9 bits constitute an offset from 3019 to 3020. Those are all in hex, so it's not, the offset is not 1, it's 7. how indirect works again. As it is going through the address evaluation stage of this thing, it takes the program counter. This is all done in here. DC is 3019. It does a sign extend on this thing, which duplicates this bit, this 0, all the way across. 9 and 7 is 16, that's 0 and carry 1, 2, 0, 3. Okay, that says go to this location, 3020. The indirect says that is not your operand. You will go down to here, and here is your operand. Okay, do you see the indirect? I mean, the name is given for a reason. You're not going directly to your operand, you're jumping there. Two-stage operation.
What gets loaded into R1 is the operand then? Or the address?
Yeah, no, whatever's in
Operand.
here
The operand.
is what's actually loaded. Yeah.
But it does a hopscotch type thing.
If we
Splinter.
put in here, this kind of a thing, this is what actually goes into the register. Okay.
So it says look in look in the keyboard status register at 3018, and then 3018 adds something to tell it to look at 3020, and then 3020 tells it to look at FE00, and then FE00 is loaded into register 1.
I think you had one extra step in there. As you go through the fetch, it's pulling the thing out of location 3018, which is this instruction. As it does that, it increments the program counter, so the program counter now has 3019 in it. As part of the address evaluation, it adds this offset to the current contents of the PC. The PC itself is not changed. Emphasize that.
And where is the offset? It's in
the instruction. This is my instruction right here.
And where is that coming from?
From your coding, as you wrote the instruction. Well, if you write the instruction in this form,
Offset is label.
the assembler is actually
Should be a
figuring that offset for you. But it's done before your program is ever even loaded into memory. See, if you write your code in this manner, and then assemble it and load it, look at it. Look at the binary that comes out of that thing. You'll see these offsets. And you should know where they come from. Because I had you write some code in binary. You had to figure the offsets. Okay, so that offset, it all depends on where things are in memory. This is just for instance. Okay. But the indirect, see, if I didn't have this on there, what would get stored into memory? Or into the register?
The address.
The FE00. Okay, that's just PC relative mode. The only difference when you put that I on there for indirect What was the operand becomes the address of the operand. That's the way it works.
So it's kind of a point. You're loading a point into
Yeah. Yeah, in C terminology, it makes this variable here becomes a pointer. That's what it is. The advantage, the thing that indirect addressing does for you, typically, if you're working up in this region, you can't use an offset to get all the way down to this thing. You cannot get an offset big enough in 9 bits to get you all the way down there. That's what indirect does for you. Yes, sir.
I'm looking at the base offsets, the LDR R1, R2, R3. So if I have like an N, I said N, R2 is 0, basically I'm setting R2 equals to 0. And I do LDR R1, R2, 3. What would that give me? Would that simply basically R2 equals to 0 before that, and I do LDR do that base offset command that you have out there? What would that give?
If you execute this instruction with a 0 in R2,
Yes.
it'll give you an error message.
Okay.
Because you would be trying to access memory location 3, which is reserved for the operating system. Okay. Conceptually, what it would do is refer you to memory location 3, 0003. But you can't get down that far because that's where the operating system routines are all stored. As for example, remember the trap instruction to get a halt? 0025. Okay, that's part of the operating system that does that halt routine, that cleans house for you when you finish up. There are other things down in those low memory addresses. But yeah, conceptually, if this has a 0 in it, all you're doing is going to memory location 3. That's what it would do. Okay. The other part of Chapter 5, of course, is the actual writing of code in binary. Well, most of that goes in Chapter 6. Yeah. So let's see. Chapter 6. Well, kinds of things that the points that need to be put over in there really has to do with problem solving. And one of the principal things there is the whole idea of decomposition. You have a hard problem to solve, you say, well, if I can get to this point, I can finish it. I know how to finish it. So now, how can we get to that point? So on, as you work through it. ultimately, that's the real point of Chapter 6. And Chapter 7 is basically to write code in assembly language. That's the only real difference.
What are we going to be expected to do for the Chapter 6 stuff on the test? Are we going to actually be writing stuff in binary?
Possibly, but it would be kept fairly simple.
Okay. Would we need to know the commands, or are you going to give us a list of the opcodes?
Yeah, the opcodes are all included, as I indicated that. Inside back cover, the ASCII codes and the instruction set are all given.
We're not allowed a cue card or anything like that, are we?
No. I'll give you everything you need. You will be expected to write code, whether you write it in binary or in assembly. You will be writing code. I'll caution you about this. If you start getting up 30, 35, 40 lines of code, you've missed something. Okay. I don't give a problem that tough. Most of them, well,
5?
I hate to put a number on it, because then somebody, when we actually do it and we're 2 over, somebody complains. But, you know, somewhere in the neighborhood of 20 lines, probably no more than that. But somewhere in that neighborhood. Yeah.
The test starts today?
Mm-hmm. And we'll run through Saturday. I don't recall that Chapter 8 was actually included, but
I
this,
think
of
you
course, is
taught
where
us
we
last
are.
week it was chapter 4 through 7.
Yeah, I think that's right. The principal concept here that you need, by the way, is this idea of memory mapped I/O. How you actually print a character on the display by storing an ASCII code into a memory location. Happens to be FE006. Just by stashing something in that memory location, it gets printed. That's a really significant idea. It was not done that way in the early days of the computer business. It was done quite differently. But it makes the I/O significantly easier to handle. Okay, anyway, that's what I see as the kind of the essential points in the test. If you have some questions, I will try. You can tell my voice is going this direction. Yeah.
Are we going to have to know the address numbers for the DSRs?
No. No, Chapter 8 really isn't even on the test. Anything else?
Can you give us like an idea, you know, what we might have to program? I mean, I'm not asking what's on the test, but just like an example.
Well, let's see.